Okay, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And I can see that we have a whole bunch of questions that were saved up from a previous time. So let's see, where should we go first? I have a question here from Mikhail. Is sociology a real science? Can it predict something? That's an interesting question. So places where science has probably been most famously successful are in physical sciences, predicting things. Originally, it was motion of planets. Then it was all kinds of things about the physical world. That's a place where mathematics, where science, aided by mathematics, has been very successful. Actually, I noticed one thing. I'm sorry, I need to do a little change here because we forgot something. Okay, so the question is, what about doing science where the entities you're dealing with aren't planets or atoms, they're people, and one's trying to deal with understanding what happens in kind of the social world and so on? Can one make a science of the same quality, so to speak, as something like physical science when the elements one's dealing with are things like people? You know, back a long time ago, I think it was in the early 1800s, there was this idea that there will be a social physics that would be kind of the analog of sort of the laws of mechanics and things that one has in physics about, you know, force equals mass times acceleration, all those kinds of things, that there will be laws like that that would govern social processes, just as there are laws that govern physical processes. Well, there were various theories. There are various theories that have sometimes had grand and not very positive consequences for the way the world is organized, there would be sort of a grand theory of how those kinds of things would work, but it doesn't really pan out. You know, when you look at it kind of on the ground and you say, are the things that people do somehow predictable, or are they fundamentally less predictable than things in physics? The actual practical experiences, they're remarkably predictable in many ways. Like, for example, if you look at people visiting websites, you get, you know, billions of data points of people clicking on these pieces of websites and going from here to there and all that kind of thing. And you can make all kinds of curves that show, you know, the average time people spend on this part of a website and how they move to other parts and so on. And you look at those aggregate curves and they're very smooth curves. They have very definite forms. And you compare those curves with the curves that you would measure in some physics experiment with particles or some other thing. And actually, those curves often look much scratchier than the curves you get from looking at how humans behave when they're visiting websites and so on. So that kind of makes one think, gosh, there should be some kind of analog of a social physics or something that will tell one things about sort of the general principles for the operation of what humans do, either individually or collectively. But and there are some sort of rules of thumb that are known, but we don't really have the same kind of framework that we have for something like physics in understanding those types of things. I mean, I suppose an area that is sort of in the middle of these kinds of things is economics, where there's sort of a question of what is the role of economics as a science-like thing. And so, you know, if you look at a typical economics textbook, there'll be a fair amount about sort of the mechanisms by which the world exchanges money and so on. There'll be a fair amount about the history of, you know, when people left the gold standard, what happened in the Great Depression, these kinds of things. There's sort of a story of what's actually happened in economics. And there'll be a small amount of theory about economics. And that theory, what is the character of that theory? That's an interesting question, because it's often sort of mocked by physical scientists, because in economics, you'll see, you know, there's this curve. Oh, it goes, you know, the demand for a product, there's sort of some elasticity of demand, and you'll draw a curve and it'll go up and it'll come down again. And somebody will say, what does the curve really look like? You know, how can you fill in the exact data points and know exactly what the curve looks like? And people say, we don't really know what the curve exactly looks like. Well, the interesting thing is it often doesn't matter exactly what the curve looks like, because what you're really trying to get out of economic reasoning, so to speak, is a sort of chain of explanation, a chain of sort of logical deduction, which just says, well, if you charge more, fewer people will buy the product, those kinds of things. And well, that's a different question from if you charge 5% more, will 2.7% less people buy the product, those kinds of things. It's something where there's a form of kind of reasoning about what's going to happen that doesn't have quite the same kind of perfect mathematical quality that one's used to in things like physics. Now, there are areas of economics where there's all sorts of sort of places where one uses statistical models in economics, and where one can say, well, there's this number and this curve and so on and so on and so on, and one can try and make some statistical predictions about what's going to happen based on that. But I would say that a lot of kind of economic reasoning is more at the level of something more like logical deduction than it is it's quantitatively informed logical deduction, more so than it is kind of something like physics, where we write down an equation and we solve it. Now, it's an interesting question. When you look at a textbook of sort of fancy mathematical style economics, and it has all kinds of equations, and there are all kinds of solutions to things, and it's all sorts of complicated things are going on, and you say, what really is this? Is it something that is like an axiomatic theory, like in some area of mathematics, where we say, assume that consumers have the property that if things cost more, they buy less of them. Assume that consumers have this kind of rational behavior property. Assume this and that and the other, where we can sort of define the world by a set of axioms and then build on top of that this very elaborate kind of mathematical structure of seeing what the consequences are. Is that what it's doing? Or is it more something that's like statistical models, where you say, we observe the following thing, and you can fit this curve by this sort of 2-parameter thing and so on? Where does it lie in those things? And I think that's not completely clear. And I think probably different people have different views about the way to think about that. So, a question that comes up in sort of these kinds of things, it comes up certainly in economics, is, can you predict things? Is it a kind of activity, a kind of intellectual domain in which prediction makes sense? Can you say something like, if a government spends an extra $1 trillion on a stimulus thing for this, then inflation will do this? Is that a predictable thing? Or is that something which is only sort of an after the fact, where we can tell a story about why it happened? I think that it is one thing to understand is that not all forms of science is the key issue, predict what's going to happen. In fact, that idea about how science works is an idea that's specific to very particular kinds of science that happened to be popular starting about 300 years ago. I mean, so if we look at different kinds of science and what sciences have predictions versus what sciences work in different ways, it's sort of interesting. I mean, in physics, the big thing was an early thing was, predict where this comet is going to be, predict where this planet is going to be. We write down an equation, we solve the equation, we can figure out, oh, this is where the thing's going to be. Then we come to a field like biology. Well, a dominant theory in biology is the Darwinian theory of natural selection. That isn't really on its own a predictive theory. It doesn't really say things about, oh, based on this theory, we know that there'll be dinosaurs for a while, and then there'll be mammals taking over and so on. After the fact, we can start saying, well, we can understand why it worked this or that way. We can reason by use of that theory, but it isn't a theory which immediately gives us, oh, we predict this is going to happen. Now, there are plenty of other fields that have at least the word science in their name, computer science, for example, not really a predictive theory of anything. It's insofar as it's sort of a science, it's a science that attempts to understand and reason about computer programs and so on. And I think that the idea that sort of science is all about, you make a prediction for what's going to happen, that's a very specific type of science. And I think that another thing to realize is one of the things that's sort of a result of work I've done over the course of many decades is this phenomenon of computational irreducibility, that even when you know the rules by which a system operates, even when you've done the most successful thing that physics wants one to do, which is, drill down, find the fundamental laws, Even when you've done that and been successful at that, it can still be the case that to work out how a particular system behaves can be arbitrarily difficult. If it takes the system, a billion steps to figure out what it's going to do, you might have no faster way to work it out than follow those billion steps. And I think computational irreducibility is something which there are only very specific kinds of questions you can ask, even in physics, that don't run into computational irreducibility. And some of the early ones about motion of planets and things like this are ones that have this feature, at least in their simple cases, that they don't run into computational irreducibility. When it comes to questions in, let's say, biology, when it comes to questions even about properties of molecules, things like that, one can quickly run into computational irreducibility, at which point it's like, well, yes, you can run the computer simulation and just figure out sort of step by step how the system works. But in terms of having a big sort of theory where you can say, I'm going to sort of put a small amount in and then jump ahead and predict what's going to happen, you're not going to be able to have that. So there's a question in sort of the social science area, to what extent, even if there were underlying laws that were known, to what extent there's computational irreducibility in how things actually work. To what extent, it's a question of great interest when people say, let's put in place this policy about how the world should work. Well, what are its consequences going to be? Well, we have, if we had a perfect social physics, so to speak, we could just say, okay, we tweak this parameter, this is what's going to happen in the world. We can decide if we want that or if we don't want that, but we know what's going to happen. The problem is there are almost inevitably unexpected consequences. That's kind of a feature of this computational irreducibility idea. You can't sort of know what's going to happen in advance, so you can't guarantee that there won't be unintended consequences. It's the same phenomenon that makes it common for there to be bugs in programs that people write. It's like, well, you think that you're writing this, but there's an unintended consequence that you consider a bug that's over here. So I think that the question of what whether one can imagine in the social domain is one full of computational irreducibility and unable to make sort of predictions beyond just watch what happens and then maybe sort of be able to explain things after the fact, or are there places where you can make predictions? One of the things that's important in science is sort of knowing what battle to fight. That is, what kind of a thing might you try to predict? I'm fond of pointing out that in Babylonian times, there were sort of three kinds of things that the astrologers thought they might be able to predict: where planets were going to be the next day, what the weather was going to be like the next day, and whether some king would win or lose a battle the next day. And, it turns out we figured out how to do the planet prediction thing. We're kind of a certain distance along the figuring out the weather prediction, but there's a lot of computational irreducibility there. And the winning or losing of battles, well, that's kind of still off the table, so to speak. And I think it's kind of the realization that there will be things that science is just not, even if you know the underlying rules, you can't figure out what's going to happen. It's an important realization in kind of understanding limitations of science. But one of the things to say is, when it comes to sociology, social science, whatever, it's like, what battle are you going to fight? What kinds of things might you talk about where you might be able to have a sensible predictive theory? So, for example, you might ask the question, I don't know, let's say you're looking at stock markets, and you're looking at economics, and you're looking at price fluctuations, and you see that, things are roughly sort of randomly going up and down, but there's a long tail here. Can you explain that? Is there a predictive theory that explains how long the tail should be? Is there a predictive theory that tells you, if this feature of interest rates changes, then this will happen, and so on? Well, the question is, which kinds of questions are you likely to be able to have answers like that to, and which are you not? So my guess is that there are a class of questions to which there will be kind of traditional science-like predictive answers. And maybe we know a few of them, but there are probably a lot more. And there are also ones where it's just not going to work. It's a story of computational irreducibility. It's not a thing where you're going to be able to make your traditional kind of science-like predictions. Now, people often say, one day there will be for sociology, a Newton of, an Isaac Newton-like figure. Isaac Newton was famous most particularly for his book in 1687, Principia Mathematica, Mathematical Principles of Natural Philosophy, book that kind of really pushed the idea of using mathematics as a way to understand the natural world. People sort of say maybe one day there'll be a Newton of social physics, and all of those web curves and all those things that describe people, there'll be some way of turning those into kind of Newton's laws type laws. And I think that if you pick the right battles, some of that may happen. I think there'll be plenty where that won't happen. And even in physics, if Newton had said, the thing I'm going to explain is the random turbulence in fluids, well, Newton would have been out of luck, because his methods and his sort of prediction in science ideas wouldn't have worked. So now, having made all these comments, I would say that just as a matter of sort of a footnote, perhaps, I happen to have been thinking a little bit about economics myself recently, and I'm particularly curious about sort of some fundamental questions like what generates value in, what makes things have value. And I kind of have a suspicion that there may be some very definite scientific things that can be said about that revolve around computational irreducibility and so on, that are not things where you're going to be able to say, and I predict the answer will be 7.4, and these kinds of numerical, quantitative, mathematical things, but where you will be able to understand this is why things work this way, and you'll be able to reason in somewhat different form about what kinds of things can happen. That was a very long answer to that. Okay, let me see. Other kinds of questions here. Well, all right, another rather philosophical one from Gisnoesis. Should we use inductive reasoning in science? That's sort of related to some of the things I was talking about. So first of all, let me explain what inductive reasoning is. So if you're doing something like mathematics, you can say 2 plus 2, we know the definition of 2, we know the definition of plus, we can say 2 plus 2 is 4. No doubt about it. It's just based on definitions of 2s and pluses and things like that. But if we say I don't know, a star that has been of the size of the sun is going to turn into a white dwarf, or if we say something about how objects that are, if we throw a ball, it's going to follow this kind of trajectory. Those are not things that we can, in the usual way of thinking about physics, at least, that we can just say, by the definition of what we're talking about, by the definition of throwing a ball and so on, we know it's going to follow a parabola. To know it's going to follow a parabola, we have to actually observe how the world is actually built. It's not something that is inevitable just from the definition of terms, or sort of a purely logical deduction. It's something where we have to deduce from the world what's going to happen. We have to throw balls a bunch of times and notice they all follow parabolas, and then say, okay, there's a general law that says that in the world, parabolas are followed when you throw balls. So there's a question of, to what extent does that work? To what extent can you say, I observe this, I observe this, I observe this, so the next time it's going to be the same way, I'm going to observe this. In physics, it's worked quite well. In some kinds of areas of biomedicine and things like that, it's a little bit questionable, because it's sort of the basis, in a sense, for a lot of the way that we think about medicine today. This thing worked for 100 people. Okay, let's try it on the 101st person. Of course it's going to work because it worked on 100 people. Well, usually, but not always. That's one in X number of people will have this bizarre reaction to this particular drug or some such other thing. Inductive inference, this kind of scientific induction didn't really work. The fact that we saw something work a bunch of times, we tried it again, and by golly, it didn't work the way that it worked before. Now, can we do any better? Probably not. Why didn't it work that 101st time? Well, because that particular person had a different genetic makeup, or they had a different, they eat many carrots every day, and nobody else in the study ate lots of carrots, and the drug reacts with beta carotene, or who knows what. I mean, all kinds of different details can be there. I think that one of the questions is, when you do an experiment in science, to what extent can you really control the parameters of your experiment? You know, in physics, we tend to be able to do reasonably well in many experiments. We tend to be able to say, we've got this isolated system, it's going to work exactly this way. When we do experiments in biology, it's much more difficult to do that. I mean, we can breed our mice to be, you know, exactly the same genetics of mice, and they've been raised in exactly the same way. And, you know, they're in this mouse colony, and maybe there's some repeatability in how the mice behave. But when it comes to people, for example, you know, we've all had different histories and done different things and all those kinds of things. And it's not going to be sort of, you don't have such a controlled setting for doing experiments. And so that means that this idea that just because it worked once, it's going to work again, doesn't necessarily work. Now, is there anything better one can do? Not really. That's the best way we know to sort of infer things from the world, is just look at what the world is like and say it's going to be more of the same. That's typically the best thing we can do. Now, sometimes we can say, we can drill down and we can say, this is what the world looks like in these cases. But actually what we know is really going on is this thing underneath. And when we've got the new thing to look at, we can say, let's look at the things going on underneath and see how those work. And then maybe we can predict a different thing here. Now, so in other words, I mean, there are fields of science. A famous example, history, you know, human history. It's like, can you use inductive inference on human history? Just because something worked that way before, will it work that way again? You know, just because no empire has lasted forever, does that mean that no empire that comes into existence in the future will last forever? Just because we see this or that happen, does it mean history will repeat itself? You know, people are fond of saying, and particularly when they talk about, you know, grand innovations in business and so on, they're fond of saying it's different this time. You know, what the stock market is going to go up, and it's going to keep going up forever. It's different this time. Usually, history does tend to repeat itself, but can we use sort of inductive inference in general to think about sort of historical processes? It's pretty iffy, because like dealing with different people in some medical study, you know, there's always different stuff going on. You know, at this time in history, we're able to start, you know, talking to people remotely through video conferences and things like that. At this time in history, you know, the way that some aspect of technology works is different. So it's different now. We're not going to see the same phenomenon that happened in the Middle Ages, because after all, now people live much longer, technology is much better, et cetera, et cetera, et cetera. Well, I think that there's sort of multiple things going on. Some of that is true, that there has been sort of change through history, but some parts of it, you know, really human nature so far hasn't changed much in recorded history. It seems like, you know, the stories one reads from the earliest stories about what humans do and do with each other and so on are pretty much the same as what we would see today. And I think those are sort of drivers of success in sort of inductive inference for history, because the human condition really hasn't changed much, but then there are other things that are different and so on. So I think it's a complicated issue where one can expect to make use of this kind of idea of, we've seen it that way before, it's going to be that way again. Now, I will make one footnote to all of this about science and the study of the use of inductive inference in science. One of the things that I've been engaged in the last year or two is trying to find a fundamental theory of physics, and it's looking like it's going really, really well. It's looking like we actually have successfully identified what the kind of low-level machine code by which the universe operates is. We don't know the details of all the rules, but we know the structure, the formalism by which things can be set up. And so essentially what we're doing is we're reducing physics to mathematics. We're saying this is the precise machine code for the universe. This is, you know, we have these sort of atoms of space and they're interacting with each other, and they have all these, the whole formalism of multi-way graphs and all kinds of things. But in the end, what it's saying is, it's just a formal thing. It's just something where, like 2 + 2 = 4, the processes by which space is constructed, time works, black holes are formed, particles exist, all these kinds of things, they're as definite and inexorable as the fact that 2 + 2 = 4. Now, it's you can ask the question, well, what aspects of our universe are kind of necessarily the way they are, and what aspects are kind of like, oh, we were given this universe, not another universe. What aspects with 2 + 2 = 4, we kind of have the idea that just by the definition of 2 and the definition of plus, the result is inevitable. To what extent is it the case that when it comes to our universe, we can say the same thing, that things are inevitable about our universe? What I'm coming to realize, and maybe I won't go into this too much detail here, what I'm coming to realize is that the answer to that is that there is, in a sense, a complete inevitability to many aspects of the universe. And there is, in fact, only one universe. And it is the way it is, and it has to be that way, and there's no other possibility. But the view of the universe and our perception and description of the universe, even the fact that we talk about things like space and time and particles and all those kinds of things, those things are very contingent. They're very dependent on us. They are our particular way of describing this single thing that is the universe as it has to be, so to speak. And so if we say, well, what about those extraterrestrial aliens who also live in the same universe? Are their descriptions going to correspond to the descriptions that we have of the universe? And the answer is no. The answer is that even at the level of talking about, oh, the universe exists in space, and there's matter and there's gravity and things like that, there are different views of the exact same thing that is our universe that will lead one to have a quite different story that one tells about how the universe works. And so in that sense, our physics is not inevitable. The universe is, I think, inevitable, but I think that the description that we make of it in the way we would describe it in physics is dependent on the way we exist. And I can kind of start seeing that by just imagining, what would it be like if each of us was the size of a planet? What would it be like if each of us was the size of an atom? How would our way of describing the universe be different? It would be very different in those cases. In the case of you're the size of a planet, things about the speed of light being limited start really mattering. You don't get to, for us normally, we look around, we see in the distance the light that comes to us from the distance that we can see. If we're not looking out through a telescope into space, the light that's coming to us has arrived in some tiny fraction of a second, some amount of time, very short compared to the time it takes us to think about what we're seeing. So for us, it's sort of instantaneous. But if we were the size of planets or solar systems or whatever, it could take hours for us to sort of know about when we move our hand, to know what happened, so to speak. And depending on our sort of brain processing speed, it could be the case that it's like, well, we're waiting. Did our finger move or not? Because our finger is off, in the position of Mars, which is 20 light minutes away, let's say, and it takes 20 minutes for one to know what happened, and so on. And so there are very different perceptions of the universe that one would have at these different, for example, sizes and so on. All right. So that was a little bit on inductive inference, inductive reasoning in science. Okay, there's a question. Oh boy. So many interesting things here. All right, I'll do one that seems extremely simple. I'm always, obviously I'm doing these things sort of spontaneously in real time. And one of the things I've discovered I learn a lot from trying to explain things in this kind of medium. And one of the things I learn is that things that I immediately say, I know the answer, I can explain that, often end up being the more complicated ones to actually explain. So there's a question here from William saying, what is a number? Okay, that seems like a dead simple question, but let's see whether I can try and talk a little bit about that. First question is, is it obvious that one should even talk in terms of numbers? Why do numbers exist? You have numbers when you want to describe, for example, multiple copies of things. So, for example, one thing that's sort of a fun, well, both thought experiment and real thing. People often say, "Oh, there are these, these are the sort of tribes living in the Amazon rainforest or something, who have languages that don't have anything, any words for numbers bigger than 3." Okay, so what's really going on there? And what I realized from talking to anthropologists and so on is, in those languages, for example, what really is going on is there's a word for one of something, there's a word for a pair of things, and then there's just a word for lots of things. And the question is, when does one actually need to start saying 5 of something, 7 of something, 11 and a half of something? When is that needed? Let's say that you have a bunch of sheep. Well, in many situations, you might just know every sheep, and they each have names, and you refer to them by the names of the sheep. At what point do you start having to say, I have 11 sheep? Well, it's a sort of stage or feature of society and civilization where you start saying, well, I'm going to trade sheep. Each sheep is worth this amount. Each sheep is worth 2 goats or something. And then I'll trade them. And then I have to start using numbers to discuss that. So I don't think numbers, it's worth realizing that numbers are something that are somewhat dependent on our kind of particular way of setting up, typical civilization and so on. And, numbers became popular back in things like Babylonian times, when people were starting to organize things into cities and so on, and people started having to have, money as a medium of exchange and have to work out what is the area of this piece of land. And, let me count out the number of things of barley or something that I'm going to get for this amount of money. Numbers became important there. The numbers that first became important were whole numbers. Then there was sort of a lot of question and confusion about what do fractional numbers mean. So, for example, in the Babylonian system, everything is in 1/60ths. So, and that's how we end up with 60 minutes in an hour, and I guess probably also 60 seconds in a minute, although I don't know whether the Babylonians had seconds. But this idea that you've got a certain amount of something, where you can have a fractional amount, it's 1/60th, 2/60ths, 3/60ths, and so on. When you start saying, well, what about the precise number, square root of 2, the precise number, which when you multiply it by itself makes 2, well, then you have a different kind of number. It's, we know that it's about 1.414 or whatever, but that number, that square root of 2 number, how do we work out what that number is? How do we think about that number? Pythagoras and friends got very confused about that for a while, because they thought every number that was worth thinking about was a number that you could get as a ratio of 2 whole numbers, a rational number. And square root of 2, they found out, is not a number that can be formed as a ratio of 2 whole numbers. It's an irrational number that isn't a ratio of 2 whole numbers. And it was at first very confusing to them that such numbers should exist. What could such a number be? What is that thing that represents the square root of 2 and is a number, but you can't sort of get your hands on it. You can't say it's the ratio of these 2 whole numbers. Well, whole numbers we sort of think we can get our hands on because we can just sort of count them out and so on. Well, in modern times, we represent numbers usually as decimals, like we'd say 1.414, 268534, etc. We have these decimal numbers, and we kind of are pretty familiar with how those work. But actually, it wasn't until the 1600s that people really started using things like decimal numbers with positional notation, and so decimals, fractional decimals, and so on. And it was actually a very confusing idea. So, for example, let me give you an example of why it's a confusing idea. Okay, so we have the number 1.000000000 going on to infinity. Okay, that's a number, great. Okay, now let's consider the number 0.999999999 going on to infinity. Is that the same number as 1.00000 going on to infinity or not? It's numerically equal to 1, that number 0.9999999 is as close as we want. If that sequence of nines goes off to infinity, that number basically is 1.000. But it isn't written the same way. But we have two numbers that are written differently. Well, are they really one number? Or are they two numbers? That's one example of a kind of a confusion, a thing that makes it not obvious what's going on with numbers when they're written as decimals like that. And in general, the question of what kind of thing we can consider to be a number is an interesting question. I mean, like, what attributes should numbers have? For example, you might say, well, if we've got two numbers, better be the case that x plus y is the same as y plus x. If you add 2 plus 3 is the same as 3 plus 2. Just a property of numbers, you might say. Anything that might be a self-respecting number should have that property that x plus y is equal to y plus x for any numbers x and y. Well, is everything that you might consider a number have that property? Perhaps not. I'll give you an example. So this is a slightly complicated example. It's the example of transfinite numbers. So it was invented by Georg Cantor in, I think, the 1880s. So this is the following idea. So imagine that you count out numbers, 1, 2, 3, 4, 5, and you go on, you keep going forever. You keep counting numbers. Eventually, let's say you've counted forever, you get a number omega. Okay, now you say, but what happens if I go even further? Well, then I get a number omega plus 1. Go even further, omega plus 2. Go even further, omega plus omega. Go even further, omega times omega. And what Cantor realized is that there is a meaningful way in which you can talk about these transfinite numbers, these numbers where the things I'm describing are transfinite ordinals, these numbers where you just keep counting forever, and then you say, well, how do I take that I kept counting forever and add more things to it? Well, one feature of transfinite numbers is that omega plus 1 is equal to omega. You keep counting forever, then you count one more time. Well, it doesn't really matter, you counted one more time. It's the same as just having counted forever, omega. But no, I'm getting this, I'm sorry, that's the wrong way around. That omega plus 1 is not equal to omega, but 1 plus omega, it's like you put down the 1 and then you go on counting forever, and the result of that should be considered as the same as just I went on counting forever. So what that's saying is 1 plus omega is omega, but omega plus 1 is not equal to omega. So it's a case where x plus y is not equal to y plus x. Now you might say, that's not a real number, that's some kind of weird infinite thing. But for many other purposes, it's useful to think about these transfinite numbers as examples of number-like things. Actually, just recently, transfinite numbers have not had a great history of being sort of useful in the real world. I recently have had a real use for them, which we'll see how it pans out. But it has to do with understanding the way that proofs work and understanding the way that infinite data structures work and all kinds of other things. But in any case, another thing that comes up with transfinite numbers, another feature of numbers is this is an interesting feature of numbers. If you have a number, and you represent the number in a certain way, if the number has a certain value, is there only one way to represent the number in a certain way? So I mentioned 0.99999 being the same as 1.0000. That's a place where our usual decimal way of writing numbers has this sort of non-canonical character, that there are multiple ways to write the same number. And you could say, well, I'm going to canonicalize, I'm going to make every number, I'm going to standardize every number. Things get trickier when you have numbers with square roots. So for example, when you have things like square root of 2 plus square root of 3, that is the same. I can't do this. I have to use orphan language to work this out, but that's the same as some other combination of square roots and things. But in general, you'll have some big combination of square roots. In general, there may be many different ways to write down. You might write square root of 2 over 2, or you might write 1 over square root of 2. And it's not obvious which of those two things are numerically equal, but it's not obvious which of those forms should be considered the standard form. And it turns out there are plenty of situations when where there is no obvious canonical form for numbers constructed by these various techniques. So if numbers are made from adding together and multiplying together square roots and things like that, you can end up with that situation. Actually, there is a way of canonicalizing those. As soon as you end up with things like trigonometric functions in the picture, you're out of that game. There isn't a way to canonicalize things that will always work. And in fact, here's an even worse thing to say. If you've got two numbers and they're written down as, square root of 2 plus pi times e times whatever, you've got some other number written in some other form, and you ask the question, are these numbers equal? Okay, so it could be the case that you can plainly see they're equal. One of them is, pi squared, the other one is pi times pi. Great, those are equal. But the thing which is an interesting mathematical fact is, in general, you can't tell whether two numbers written down that involve square roots and trigonometric functions, things like that, whether these two numbers that are written down are actually equal. You could try and work them out numerically, and you can say to 100 digits of precision, these numbers are equal. To 1,000 digits of precision, they're equal. Are they exactly equal? Are they the same number? Well, in order to tell that, you would have to make essentially mathematical transformations. You would have to do things like saying, if you have sine of 2 times some number, that's the same as 2 times sine of the number times cosine of the number. Those kinds of things that are exact mathematical transformations. And you might say, well, I've got these two numbers. Is there a chain of mathematical transformations that I can make that take me from one number to the other? Then that would prove that those two numbers are equal. Well, the problem is, and this is a consequence of Gödel's theorem and a bunch of other things, that there is no limit on how long that chain might need to be. It might be the case that these two numbers that are written down are in fact equal, but that chain, the minimal chain necessary to go from one number to the other, is an arbitrary number of steps long. It might be 1 billion steps. You might have to go through, it's like doing a mathematical proof. You might have to go through all these different gyrations to show that these two numbers are equal. And in general, there just isn't an upper bound on how long that chain needs to be. So that's a sense in which numbers might be equal, but you don't know they're equal. So there are a lot of tricky things that can go on there. So that's a now, by the way, some of these things about whether numbers are properties of numbers. Let me give you another example. In a computer, there is this idea of so-called machine arithmetic. Personally, I actually think it's a pretty bad idea. I think a lot of kind of wrong things were done in the 1970s about how that was set up, but it's kind of the standard way computers work now. So when you have a number like, I don't know, you're trying to represent 1/3 in a computer or 2/3 in a computer. Well, how does it actually get represented? It's more or less, it's 0.666666666. It's actually in binary, not in decimal, but at least on most computers. Then the question is, how many digits do you actually store in the computer? And the point is this computer only stores a limited number of digits. It's usually about 53 digits in binary, something like that. And that is, it's a so-called floating point number usually. So it stores the number, and then it stores times 10 to the power something or other that gives the scale of the number. So in any case, when you do that, you can ask questions like, when you store numbers to only a limited number of digits, is addition commutative in the sense that x plus y equals y plus x? Well, it's not. Is it associative? Brackets, parentheses, where parentheses go and plus signs don't matter. It's not. So in other words, some of these things which are features of when you make this sort of finite precision arithmetic, are those things that you have in a computer, those machine numbers, are they in fact genuine numbers, or are they some weird other thing? They're a little bit weird. I'll give you another example. If we have 1/3, so 1/3 is decimal 0.33333. When a computer represents it, it's representing it in binary. So it's representing it just with 0 and 1 digits. And so it's, I don't remember what a third is in binary. I should be able to work it out. 0.11, 0.101, 010101, something like that. I'm not sure. In any case, one of the features of that is when you might want to have the property that the thing that represents 1/3 for you, when you multiply it by 3, should be equal to 1. Well, turns out that won't be the case. And when you truncate it to a finite number of limited number of digits, you can end up with a situation where the thing that represents 1/3, you multiply it by 3, it's 0.9999998, let's say, not exactly 1. And in fact, for a while, people used to make computers, particularly for business applications, that used so-called binary coded decimal, which was kind of a weird, hacky way of kind of packing decimal digits into triples of binary digits in order to avoid things like 1/3 times 3 not being equal to 1. But so machine arithmetic on computers is an example of where you're sort of thrust into the question of, are those machine numbers really numbers? Do they have the properties that we expect of numbers, and so on? There might be more to say about that, but that's a little bit of on the question of what is a number. Let's see. Gosh, a lot of wow. Okay. Should I talk about here? Let's see. Well, there's a question here. I'll maybe try and do this. A question here from Memes of Destruction. Would computer processing speed increase if we had a compendium of mathematical proofs? Okay, it's an interesting kind of question. So what do mathematical proofs tell us? They tell us they tell us results about mathematics, where in principle, if we knew the axioms of mathematics, we could go through and rework out those proofs ourselves. So in other words, if we're told certain facts about arithmetic, let's say, we could in principle go and work out everything we need to know about number theory and this and that and the other. But in practice, it's been centuries that people have been working out all those details of mathematics, and they've been able to say, actually, if we go in this direction, we can get this big, complicated result, which we can write down, and you don't have to repeat all of those steps. You just, here's the result, great, be happy. Well, and mathematics progresses by taking those results, those theorems people have proved, and saying, let's see what else we can prove by building on top of those theorems. Now, it's certainly not the case that we're exploring all possible mathematics. We're making these kind of highways of mathematics where we're going from a theorem we can prove to another theorem we can prove, and then that one lets us build another theorem. Maybe better to call it a tower of, where the various bricks in the tower are these theorems we proved, and we can keep going and we keep going, building on what we've already built. If we say, okay, we actually want to know about this mathematics off in this way different direction, it's like, sorry, you're starting from scratch. You've got to start from the axioms and start proving things step by step. Okay, so there's a similar kind of question for computer programs. So if you write a program, you can, it could be the case that you've written this whole big blob of code, and actually somebody looking at that blob of code could say, you didn't need that whole blob of code. It's just, x plus 1. That whole blob of code you've written just turns into x plus 1. That would be kind of a theorem about your code that says this whole big thing is just x plus 1. Let me give you an example. Let's say you have a function reverse that reverses the elements in a list. So it turns ABC into CBA. Okay, so if you say reverse of a list, that the result of that will be, you just get back the list you started from. It'll reverse it once, it'll reverse the reverse, that gets back to what you started from. So it's a theorem of programming that reverse of anything is the thing, okay? So you can imagine these kinds of things that are a little bit like mathematical theorems, but they're instead theorems about, they're computational theorems about a programming language, a computational language, whatever. And so you can imagine building up a library of those kinds of theorems about programs, which are analogous to, not quite the same as mathematical theorems. The world of mathematical theorems is quite divergent from most of what one will be interested in for computational theorems, but one can build up these kinds of computational theorems. And actually, when you compile code, when you're taking code that you write in Wolfram language and it's getting compiled into some low-level machine code or whatever, what's happening is there are lots of those theorems that are getting used. There are lots of theorems that say this thing will always be an integer. It could never turn into a pair of integers. It will always be an integer. So that means you can always represent it in the computer in this way. And that's a theorem, so to speak. And so what has to happen when you are trying to say, how could you, is it good enough to just use a single integer to represent this whole thing in this computation? Well, you can prove the theorem that it is. Okay, so the question is, if we had a big library of those theorems, how successful would that make us in being able to, for example, even execute our code faster? Because if we could say, forget running this piece of code, there's just a theorem that says the answer is 7, then we don't have to run the piece of code. We just say the answer is 7. Okay, so here's the problem. The problem is, if the code was worth writing in the first place and worth running in the first place, then there can't be a theorem that shortcuts it. If the only way there could be a theorem that shortcuts it is if actually that code was sort of, well, you wrote it in a very elaborate way, but you didn't really need to write all that stuff. You could have just written this short thing here. Now, you can be in a situation where, yes, you could have written that short thing, but you don't know that. You, as you're thinking about it, you imagine it in this much more elaborate way, but actually it turns out that was you didn't need to do all that stuff. It was actually really much simpler. So that's a sense in which one can imagine sort of a computational theorem being useful, but in general, those things will be less useful than you think, because it sort of wasn't worth writing the program if you can just jump ahead and say this is what the answer will be. But there are some limited places where it's useful, particularly in compilation, where you're saying, does this program that I wrote fit into this thing that can be represented at a very low level on this computer? And that's the thing where if you have a theorem that says it works this way, you may be able to do that. And if you don't have that theorem, you won't be able to guarantee that you can do that. But this whole question of whether it's important to have a sort of library of mathematical theorems, I've been very interested in this. There are about 3 million theorems that have been written down in sort of the history of human mathematics and published in papers in the history of human mathematics. And I've been very interested in representing those theorems in a kind of computable way as something where when we build up mathematics, for example, we can start to say, has something like this theorem been seen before? Let me search in the set of theorems and identify that and keep going. That process is actually very difficult of curating theorems, because we kind of have to have a very standardized way to represent these ideas of mathematics. And that's something we built a long way in that direction with Mathematica and in Wolfram language, but there's still further to go to represent sort of all the mathematics that's been done, particularly mathematics that was done after the beginning of the 20th century, that sort of diverged a bit from mathematics that had been done before. Well, let's see. People are asking such elaborate questions here. Well, okay, there's a question from Parmenides. What's the worst computer bug you've ever had? What was the simplest computer bug that you couldn't figure out? What is a bug and why do they happen? When you write a program and the program can do lots of things, it's basically impossible, both as a practical matter as a human and even theoretically, to know what could this program possibly do. And in certain, if, for example, you might have a program that's trying to do some particular kind of computation, and you know that you tested it for 1,000 inputs, worked great. Okay, now in real world, somebody is giving it a weird input. Oh, it breaks in some crazy way that you never could foresee. Actually, someone was asking before about scientific induction. It's an interesting case. Software and software quality assurance is an interesting case of that. When we build Wolfram language, for example, we do lots of quality assurance. We do lots of testing. And so every time, every day we're building new sort of prototype versions of the language, and every day millions and millions of tests are running on these versions. And we're saying, did the results come back the same as they came back before? Are they If they were correct before, are they still correct, and so on? That's often a very tricky thing to answer because there'll be details that might be different. This pixel might be in a different place on the screen because something changed about the way the operating system did this or that, yet it's still correct, even though it isn't identical, so to speak, to what was before. But nevertheless, you can say, if the tests work, does it mean that the code is correct? And then you can say, and obviously the answer is no. The sort of scientific induction answer would be, if you ran enough tests, well, then you know how the thing is going to behave, but it isn't true. And that's, in a sense, one essence of bugs is the fact that that isn't always true. Now, you can say, people talk about program verification. Can you prove the theorem that this program is always going to do the right thing? The problem with that is the definition of do the right thing is usually hard to make. If the definition of do the right thing is, oh, it doesn't start scribbling on memory that it wasn't supposed to be allocated, or does it, could it ever run forever and never halt? Those kinds of things. Those are definite things where you can imagine trying to prove these theorems. You might not be able to do it, but you can imagine trying to prove these theorems. But if the question is, does it give the right answer? Well, how do you define the right answer? The right answer is probably pretty much defined by the piece of code you wrote. That is what you're trying to do. And so that's defining the right answer. So it tends to be the case that you get into this very circular situation of saying, how do you verify that the verifier is correct? And really, the thing you're writing, the original program you're writing, is the program that specifies what you want the program to do. Now, in practicality, there are plenty of situations where there can be a bug which is obviously wrong. Like you're running your program and it crashes. You're running your operating system and it freezes. You're trying to, something is supposed to remember your login and it forgot it. These are things where, it's pretty everyday to say that's wrong. And you have, but let me give you an example. I've been studying some abstract systems last week or two, things called tag systems. I'll write something about them soon. And these systems have the property that they're very simple systems defined by very simple rules. And the question is, you run these rules, and eventually the rules stop applying and the system just halts. Okay? Well, the question is, does it always halt? And the answer is, I've got examples where it takes 202 billion steps and then it halts. I don't currently have any example where I can prove that it doesn't halt. But I don't know whether it always does halt or not. That's a difficult thing to determine. And if I had a program where I'm just going to assume as a programmer, I'm just going to assume it halts, it's like, actually, I don't know that. And there probably is no proof of that. There may even theoretically be no proof of that. There could always be an escapee, a kind of a version of the input where it won't in fact halt. So that would be an example of a very nasty, insidious kind of bug if I made the assumption that it was always going to halt. But as a practical matter, well, let's see. I mean, when I write code in Wolfram language, which I do every day, I would say that sort of bugs are not as common as they might be, partly because what I tend to do is, because our language is a symbolic language, it means you can take apart any program into its component parts, and those parts can run perfectly well. It's not going to say, if you have a low-level programming language and you take a lump of code out of the middle of a program, you have to build a whole harness to run that piece of code. If you have a symbolic language, then any piece of code just takes symbolic expressions as input and gives symbolic expressions as output. So you can take any subpart of a program and expect it to run separately. And so it's much easier to debug things in that situation. And it makes it, now you end up writing more ambitious programs, but still my experience tends to be that when I'm writing Wolfram language code, it's not super hard to debug, because I can take pieces out and so on, and just see what they do, and I can put sort of diagnostic things in to make sure it's doing what it should be doing, and so on. The places where things get much more difficult to debug, when you're dealing with computer systems, and when you're dealing with particularly things where there are multiple computers involved in sort of orchestrating together, making things happen. So for example, in cloud computing, in our Wolfram Cloud, for example, that's a large number of computers, and they're all kind of working together to deliver results to users and so on. And there can be very complicated and insidious bugs. So there's one that I wrote about a few years ago, actually, that was a bug that you make a request to the cloud. Usually it works very fast, but sometimes it's really dog slow. Used to be the case. Okay, what's going on? What's going on? Well, the team was working on this. They looked at it for ages, and it's just, we can't figure out what's going on. Okay, so I eventually decided I better look at this thing. So I started looking at it, and I started plotting, you make 1 million requests, some fraction of them are slow. Let's plot out both when the slow requests happen and how slow are the slow requests. So I discovered this really weird thing. I don't remember the numbers anymore, but when it was slow, when it was fast, it happened in 50 milliseconds. When it was slow, it took 200 milliseconds, let's say. But sometimes it also took 400 milliseconds. And sometimes, even more rarely, it took 600 milliseconds. So the question was, how could there be something where it, actually, the other thing was, it was quite common for it to take 200 milliseconds, but sometimes it only took 50 milliseconds. So that right there is a tremendous clue, because if you're asking a computer to do something, usually it takes 200 milliseconds, but just sometimes it happens in a quarter of that time. There's 150 milliseconds of time wasting going on, because otherwise, for it to even be possible for the computer to answer you in 50 milliseconds, that has to be something the computer can do. So, but in any case, the most bizarre thing was that the delays were quantized. It was either 200 milliseconds, 400, 600, 800 milliseconds. They were in lumps of 200 milliseconds. I'm not sure if I remember correctly the 200 milliseconds, but let's use that for the sake of this description. But so it's like, what on earth is going on here? And well, it turned out, trying to remember all the details of this, but it turned out I started tracing down exactly what was happening. Where was the slowdown happening? What program was actually running when the computer was taking these 200 milliseconds and so on? It turned out to be inside the Linux kernel of the Linux operating system. It turned out to be in little pieces of code that have to do with the device drivers, the Linux operating system kernel. It was deep in the low-level sort of nervous system of the computer. It wasn't like, oh, that's code I wrote. It must be, I made a mistake. It was deep in the low-level code of the operating system. So like, how could this be happening? Well, I have to say, I asked friends of mine who work on sort of low-level operating system things, and they said, oh yeah, the device drivers in Linux, they're terrible. It's like, but that's the most common operating system used in the world. How can you say they're terrible? Well, it's just an open source operating system. It's not very good, but whatever. But that's just one of the funny things that happens in the world. But in any case, the point was, this was a very well-trafficked piece of code, and there was something going wrong with it. In the end, it turned out, I went through a whole chain of debugging of whether it was to do with file system access, whether it was to do with all kinds of other things. It turned out to be a stupid problem that some other part of our infrastructure was sending all kinds of interrupts into the operating system, asking it to do other things. And the operating system was like, oh, let me look at that interrupt. Oh, let me look at that interrupt. And it was wasting time doing that and wasn't sort of concentrating on the task that had actually been given. But that was that took a couple of days to, maybe a day or two to debug. Once one had gone in and really tried to do sort of data science, saying, let's look at billions of queries and see what's happening and so on. I mean, I could tell you many, many, many other debugging stories. I would say most of the debugging stories that revolve around me are, it gets to me when it's really been a nasty bug and it's taken months and people have been very confused. And eventually I say, as a very, I would say at some level, ultimately hands-on CEO, it's like, let me see if I can actually understand what's going on. I could tell you one other story like that of more recent, a couple of months ago, again, something to do with our network connectivity. We could tell that certain network accesses were slow, and it was affecting a bunch of our cloud infrastructure. And it's like, what's going on? And people are saying, well, some of our network accesses are really slow. And some of them aren't even connecting at all, but some of them are really slow. And it's like, we don't know what's happening. This is some kind of connection that's flapping, and it's, sometimes it's working, sometimes it's not working, what's going on, et cetera, et cetera, et cetera. That one took a few hours to debug, but that one, what I eventually noticed is, let's just take all of these queries and see, we got a query, it's going to this particular IP address, this particular place on the internet. We got another query, it's going to this particular place on the internet. Which of these queries are slow and which are fast? Let's just get a bucket of thousands, millions of these queries, and let's just see if we can tell what's the difference. Is it consistent? The ones going to a particular IP address are slow, and ones going to other IP addresses are fast. So it turned out we discovered that it was a problem with the way that a very upstream internet service provider was passing traffic to another large internet service provider, but just one particular provider. And all the other things went through just fine, but with that one particular provider, it was blocking it for some reason, or it was incorrectly connected. And so it looked like, well, most queries are going just fine, but some are not working. Turned out it was a very consistent set that weren't working, but it wasn't quite as consistent as you might have thought, because some of these places that the queries were going to had multiple different exposure points on the internet, and so they could go through different paths and so on. But in any case, that was an example. But usually, I would say that these kinds of bugs in computer systems, these are complicated, and my observation is that solving them, it's a big part of the story is use kind of data science type methods, use computation to solve these bugs, take in large amounts of data, actually analyze it, make graphs, plot out things. Don't just try and do the thing that people so often do of say, let's look at the log file. Let's read through 10,000 log messages and see if we notice something going on. Us humans are not that good at that. Have a computer do it. If necessary, and I've done this too, use natural language processing or use various kinds of machine learning on log files to go and figure out where are the anomalous pieces of these log files. Can you figure out what's happening? And there's a decent chance you'll succeed at doing that. But those are some kinds of things. I mean, I would say there's one bug right now that we're probably going to fix, because we have some very old hardware that we're using for some of our services. And we're probably going to just fix it by buying new hardware. But there's a bug where certain kinds of process restarts are running out of memory, or at least they report that they're running out of memory. But when we look at how much memory they seem to have enough memory. And that's one where I've been telling the team, this is, again, just go look inside the operating system. You can go read the code of the operating system and say, but we don't really want to do that. But look, we can see there are 10 places where this particular message that we are getting can be generated. You might think, oh, if you can read the code of the operating system, just instrument them to see what's happening. It's vastly more complicated than that, unfortunately. And it's not so clear what's going on. But this is a case where it's like, we'd kind of like to debug this, but in the end, it's probably not worth it, because we need to buy new hardware anyway, and the new hardware will almost certainly make this problem go away. Another type of problem, I could talk about many of these. So here's an example of a type of issue that's pretty complicated. Is let's say you have 1,000 computers, and you have zillions of people who are trying to make requests of those computers. Request comes in, you have to say, okay, computer number 217 is free right now. Let's send the request to that computer. Okay, another request comes in, another computer is free. Let's send the request to that computer. Okay, let's say most of the computers are working on something, and you want to know, which computer should you queue up a request to which computer should you, if you're sending successive requests to different computers, which ones should you send them to? That's a problem of so-called load balancing. You don't want kind of, well, it's also relevant if some of these computers are connected to the same memory subsystems, connected to the same networks and so on. You don't want to sort of make this particular set of computers really, really busy while these other ones over here have nothing to do. You want to sort of spread the load over these different computers. So there's a complicated kind of issue of load balancing, of how do you send successive requests to different computers. And so there are different strategies, like least recently used might be a strategy, which is to say, okay, the request that comes in, send it to the computer that was least recently sent a request. Another thing you might do is to say, well, which computers have finished, which computers are are almost finished with the requests that they're running right now, so we can queue up a new request to that computer. Well, the problem with that is, depends on what kind of requests they're dealing with, because maybe those requests, let's say real case for us, are Wolfram Alpha queries. Wolfram Alpha queries, the query might be a really easy one to answer, but it might be really complicated to answer. So it's very hard to know how long that request is actually going to take. So if you get queued up behind some request that's going to take 5 seconds, you're in bad shape, because your request is going to be waiting for 5 seconds to be done. So it's kind of a complicated thing to figure out the strategy of how you should do this kind of load balancing, particularly when you have these very variable and very unpredictable amounts of time that will be spent on different requests. And so that's a place where, we've had all kinds of issues in figuring out the optimal way to do load balancing. I'm afraid the main result of theoretical load balancing discussions is any fanciness isn't going to help you. Anything you do where you're trying to be very fancy about predicting this and that and the other, in the end, sort of computational irreducibility bites you. And in the end, just the kind of most simple-minded approaches tend to be the most robust. And that's the thing we've actually discovered in practice more often than we might like. Let's see. Well, okay, let me do a couple more here. There's a question here from Red Lantern. How quickly is technology advancing at the moment? Is science reliable in the grand scheme of things? Okay, this question about how quickly technology is advancing, it's often fun for me to talk to friends of mine in technology industry and so on. And some people are like, there's a singularity, technology is advancing faster and faster and faster, and it's all exponential and so on. And then there are other people who are saying, I haven't heard a new idea in years. So how can both these things be true? Well, I think one point is that what tends to happen in the advance of technology, as in science, is that some new methodology typically is invented, some new kind of direction is defined. And then a lot of stuff happens in that direction for a certain period of time. Machine learning starts to be real. Okay, for a decade, really interesting things get figured out there. Computer graphics starts to be good. For a decade, really interesting things get figured out. There's lots of visible progress. The idea of social networks gets developed. There's lots of progress there for a certain period of time. The idea of laser printers gets invented. There's lots of progress for a certain period of time. But if you say, given the areas that you already know about, how much progress is there? The answer is, by the time you know about it, and particularly if everybody knows about it, there probably isn't that much progress that's going to happen, because it's kind of something where it's had its 5 or 10 years of sort of rapid progress from this sort of methodological advance. And so it ends up seeming like, if you say, let me take this set of things that I already know kind of what they are, and then say, is there lots of progress in those? Well, the answer might be not really. The progress happens because new things are invented that are things that were quite different from the things you already defined. So a very typical thing is there'll be some domain. The domain will develop to a certain point. People will say, we really want to, recognize progress in this domain. Let's set up a prize for this particular domain. The best physics, the best, social network, the best whatever. Okay, pretty much, I think it's a fair statement that as soon as there's a prize for something, the most fertile period is probably over. Because as soon as you can bucket it to the point where you say, there's this definite thing and there's stuff happening, and there's incremental progress happening, but the places where it's really going to look dramatic and really exciting and really different, really unexpected, real progress happening are the places where there wasn't a prize set up yet, because nobody even thought that was a thing yet. So I think that what one sees is there's sort of when you define progress in a particular way, then inevitably it tends to slow down. If you're sort of open to progress can be sort of anything, and it may even be a different definition of what we mean by progress, then yes, there's sort of an infinite frontier of possible things to discover and invent, and it looks fast. And I would say that in my, I've been sort of paying attention to technology for, oh gosh, probably 50 years now. And and there are things where it's like, wow, this is happening very quickly. And it's like, oh my gosh, I can't believe we're still at this stage. 40 years ago, we were at a stage just only a tiny bit before that. So I think there are particular areas where there will be, no doubt, rapid advances in technology, and others where there won't be. I mean, like, for instance, I don't know, smartphones. There was a period of rapid advance, and then it's like, do I really need a new phone? Do I really need a bigger camera? Laptop computers. Do I really need that extra little twiddle? I don't know. It's not. It doesn't feel like it's dramatic progress. But at the beginning, it was certainly dramatic progress. So I think this is something one can expect to see. And if one's picking a particular domain, the thing may get worked out, and there may be only incremental progress. If one is sort of open to all possibilities, then things will tend to look like there's more and faster progress. And I think yeah. Let's see. I'm going to do one more. Okay, a question from Adit. Says, I'm 16, reasonably intelligent, this person says, but nowhere even close to genius. Hard to know. I lack the self-belief to achieve my dream, very successful career in AI. I feel I'm not smart enough. I feel that all people there in the community are geniuses, and I feel like I cannot make it so. How is it possible to overcome this kind of self-doubt? Well, that's an interesting question. I think that there are lots of different ways to succeed, make progress, discover things, invent things, whatever else. And I think one of the things, different people have different kinds of skills and different ways of doing things. Some people, the best thing for them is sit by themselves and try and figure stuff out. Okay, they'll come up with something great. Maybe for other people, it's like, be part of some team, maybe even be the leader of the team. It's like, you're not very good at the actual mechanics of making the thing work, but you're pretty good at figuring out what should be done. And, and then if you can work with other people to actually actualize what you're talking about, then everything works well. I think that sort of part of the first step in, doing something where you achieve something you're excited about. And by the way, the kinds of things that different people are excited about may be completely different. And it may be that somebody's, I really want that achievement, is somebody else's, I couldn't care less about that, and vice versa. So, if the achievement you want is to discover something interesting about, let's say, AI, what do you mean by interesting? Do you mean lots of people are going to use it? Do you mean it's going to be something that is going to be intellectual progress that academic papers get written about? Do you mean it's going to be some different kind of thing where that there are different definitions of success? And in terms of what it takes to achieve those different definitions of success, there are also typically many paths to those things. And I think that the number one issue is sort of defining what the objective is. In other words, if you say, I have this great idea and I have this great thing that I want to achieve, then it's like, okay, how do you take the steps to achieve that? But even just this act of saying, I've got this great thing I want to achieve, and defining that thing, that's a very important step. And if you can do that, you're already kind of way ahead, because just knowing, well, if I do this, I do this, I do this, then I'm going to make a great discovery or whatever. It's just not really the way that, there's not sort of a procedure. There's not a kind of set sequence of steps that people take to get to the point where they can do something sort of unexpected and something that they consider to be an exciting achievement. So I think I would tend to feel that, well, also there's this question of you mentioned that sort of everybody in the community around you seems to be sort of a genius, and how do you fit into this? I think that is, I don't know. I'm not sure that the comparison of people in that way is particularly productive. And one of the things I've noticed, I suppose, some parts of the world, maybe Silicon Valley is a particularly bad example of this at different times in its history, is, people will always make themselves out to be a lot more geniusy than perhaps they really are. It's like, let's use a complicated word when a simple word would work just fine, but it makes it sound more geniusy if we use a complicated word, and then the person you're talking to doesn't know what you're talking about. And sometimes that's usually, in my observation, usually, but not always, a bad sign. I mean, there are people where you talk to them and they only talk in very complicated words, and it's like blah, 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 blah. And it's like, how can this be something real and interesting? Then you pick it apart and you realize this person is pretty bad at explaining things, but what they're saying is really very interesting. And that can happen. But it's I think, it's not just because there are fancy words used doesn't mean that the thing being talked about is fancier, so to speak. And just because there are simple words being used doesn't mean that the thing that's being talked about is necessarily sort of mundane and simple. And I think somehow my observation is that well, since I like to work in a lot of different kinds of fields, I am constantly in this situation of feeling like there are lots of people in this field who are a lot smarter about this field than I am. How can I possibly make progress in this field? Except somehow I managed to do it a whole bunch of times. How can that be? Well, what are some examples of things that happen? One thing is the experts in some particular area, they tend to know, they know exactly what to do. And they're in this path and they're running around and they know what to do because they're experts. But they're not looking at some bigger question, something that maybe comes from outside their field, that suddenly it doesn't work to just make that little sort of micro path. There's suddenly this other thing that you can make progress with. And you don't feel as smart as the people who are experts in that field, because they're telling you all these complicated things about this field, and what about this? And you're thinking about this. Well, surely you can't be able to do that because of this footnote that says this and that and the other thing. And it's like you could come to the conclusion that no, it's hopeless. I can't possibly do anything in that area. But actually, somehow it often seems to work out just great. And I think it is worth knowing a certain amount about these areas, but if you drill too deep and you get too involved in, the minutiae and what about this, what about that, you can easily lose sight of whatever big picture you potentially can get to. But I think that a thing that's worth realizing is, particularly if you try to work in a sequence of different fields and you try and make contributions in different areas, I can say, at least from my own experience, one is continually finding oneself pretty humbled by the kinds of things that people in those fields already know. Like, for example, I mentioned earlier here that I've been thinking a little bit about economics recently, and I don't really know anything about economics. And I've sort of heard about it for years, and I've kind of known lots of people who've been distinguished in that field, and I've kind of looked at the pictures and the textbooks, and I've kind of seen people use our technology to do things in economics, but I don't really know economics in the sense that, if I was doing some, standardized exam about it, I think there'd be plenty of questions where I wouldn't know the answer. And yet, how can I be thinking about doing something that might have significance in that field? Well, I think maybe it's just pure, confidence or arrogance that one can do this, except that it has worked for me many times. So I don't think it's completely a misplaced idea. But I think the point is that, yes, there will constantly be people who are experts, things to know that you don't know. The question is, can you define what your objective is well enough, and at least learn things enough along the path that you need to go on that you can be successful in achieving that path? And I think, in terms of the personal question of how do you conclude that you can do it versus not, I think that ends up being a thing that comes mostly from inside one. And I've been fortunate in my life that I worked on a bunch of different things. I started out doing sort of things when I was pretty young that were reasonably successful. And, I started writing physics papers and things like that when I was a teenager. And, they worked out just fine. And having had certain successes, you build confidence to say things like what I'm saying now, which is I can just sort of walk into this area of economics, let's say, which I know, little about, and make a useful contribution, so to speak. Now, you kind of build up after probably decades to that level of either confidence or arrogance, depending on how you look at it. And I'm not sure that that's the place you start. And I think that a good place to start is, you pick something that's a pretty modest objective, and perhaps you pick something which is out of the mainstream of, oh, everybody's working on AI and they're trying to solve this problem and that problem. Or pick a problem that seems like it's a little problem off on the corner here that isn't something where there's thousands of people working on that. And there's don't pick the problem of, for example, a robot grasping at something, which is a very difficult kind of AI-like problem, because zillions of people are working on that. If you pick a problem that's a little tiny sub-problem of that, that's still kind of interesting, like, how do you pick a particular kind of fruit or something? How do you make a robotic manipulator that picks a particular kind of fruit? A bad example, but something like that. And you kind of get yourself sort of completely around that particular thing, which perhaps nobody else cares about right now, and then go solve it. And that kind of builds you a certain amount of confidence. And yes, I can actually solve these things. And then you go for the next thing and the next thing and so on. The issue of solving things which are sort of out of the main, out of the sort of main path, main track, is sometimes you'll solve those things and you'll be very satisfied. Yes, I solved it. I come up with this really great solution. Oops, nobody cares about this. Well, then you have to convince people they should care, or you just take it as something where it's like, well, I figured this out. I learned something from doing this. I got satisfaction out of doing it. It's like I put it in this little, wrap it up, tie a bow, put it, tie it in a bow, and put it aside, so to speak, and then go on to the next, perhaps bigger thing. Anyway, that's a that would be my comment. I think the concept of it's a very personality dependent thing. If you say, I'm going to set myself up for this thing, I'm going to try and do it, maybe it's too hard. And if you say, well, maybe I'm going to fail, you keep looking down. You keep saying, maybe I'm going to fall. The chance of falling is much higher. I think many people, like myself, for example, who work on big, complicated projects, it's like, this thing isn't going to fail. I don't even have to think about it failing. It's going to succeed. And, by golly, maybe the original thing that I was originally hoping might happen doesn't actually happen. But, but it ends up being the case that one navigates to something which is a good result. And I think that the thing that so that this kind of, but what if I fail type thing tends to be rather, it's like just pick something where you're pretty confident. Even if it's small, you can get yourself to the point where you're pretty confident you can do it, and then just try doing it. And you also have to think about, okay, if you fail, you try and do some project and the project doesn't work out. Maybe you didn't even tell anybody about the project. Okay, it's a pity it didn't work out, but it's not terribly embarrassing. It's not, there's not, maybe you wasted a little bit of time. Maybe you learned something doing it. It doesn't have a high cost. So I think it's one of these things where if you can define what you want to do, and it's kind of like just try doing something. Now, I will say that if you say, okay, I'm going to build a general AI, I'm going to solve the problem of artificial intelligence and things, that's probably not a great problem to work on. I mean, if you think, I would pick a more specific subproblem that is one that hasn't necessarily been worked on a lot, and I would kind of, get all over that problem. And, just a sort of thing, I'm going to sit and invent the great new theory of everything, it's kind of not the way it works. It's kind of when you imagine, I mean, you have to, when you work on big projects, you end up making many sub goals for those projects. And if you're not experienced at doing really big projects, it's not a great idea to just say, I'm going to do this huge project from the beginning. Better idea to pick a smaller project where you can readily sort of see your way to where you want to get to. And it's, I mean, in my efforts, for example, in finding the fundamental theory of physics, okay, that wasn't a thing where I sat down when I was, I was thinking about things like that when I was, 15, 16 years old, but I wasn't sitting down with a blank sheet of paper, would have been paper in those days, saying, I'm going to write down the fundamental theory of physics. I didn't expect that was going to work. Instead, it's sort of a 40-year journey that involves doing many specific concrete things and then realizing, oh, there's this particular piece of progress that can be made and it has these consequences. Let's go for that. Oh, there's this particular thing that can be done. Let's go for that. And I think sort of being concrete in these goals is important. Defining kind of defining the goals, as I say, I think is the most important thing. Figuring out the path by which you get to the goals is typically easier than defining the goals. But don't imagine that the goals should be, solve the general AI problem starting from a blank sheet of paper. That's not the right kind of goal. Pick a goal that is much more modest. And if you're going to make a mistake in picking the goals, make the mistake on being too modest in the goals. Have something that's really, you're like, I know I can do this. It's only going to take me a week. And, I really know, rather than, I don't know how I'm going to do this. I'm just imagining it, so to speak. I think that would be my suggestion. All right. Well, lots of interesting questions left over for another time. And thank you for the diversity of topics and questions you've been asking. I have lots of fun talking about these kinds of things. And I hope you find this interesting. And thanks for joining us, and see you another time. Bye for now.